Hello everyone. Hope you can hear me. Yes. So, can I get a confirmation that you can hear me? Hello. Can anyone confirm whether I'm audible?
Yes, sir.
I hope my screen is also visible. Let's start with today's discussion. So today's discussion is based on week 9 lectures for the course Computer Vision and Image Processing. Uh, so how did the week start? What was the core idea of the week? So we wanted to get some interest points in the image. Using those interest points, we have many applications on which we can work on. So directly using images can be very expensive, but if you have some interest points, you can represent the image with those interest points and then do further post processing of what specific application you want to do. So what is an interest point? Anyone? So any idea why do we call that interest point? Why what is something really specific about it? Just in general, not a formal definition. So, for instance, if I have an image like this, maybe I'll just draw some random image, but that image has this specific house out there. So, what do you think would be the interest points? So, these intersection of edges or the corners are interest points. Why? Why is it so? Because if I try doing just plotting the points out there, I am able to get some rough idea of what the figure is. Of course, it's not exactly true that just with those specific points you can easily identify the image, but you can get some idea of what the image looks like. So that's why we need some specific points that we call as interest points. Once we extract those interest points, we can make use of it for further processing. So the properties that we desire for these interest points is what? If I give you a rotated image like this, then whether the rotation changes anything? Do you want it to change anything as such?
No.
Uh, Nothing should change if you rotate the image.
Positions of this interest point will change, but
Okay.
interest point will remain same.
Yeah. So if I rotate the image, the interest point should also be equivalently rotated. That's what you're trying to say. Yes.
Yes, sir.
And same with the, what do you say? Same with scaling of image. Or if even if I change the illumination, for instance, if I take this image in daylight, where you can clearly see the interest points, assuming that you're not facing the sun and your camera is able to capture the image properly. And at night, if there is very dim light, for instance, a street light is out there, you are still able to get the same points out there. So, what interest points, what are the features, characteristics that we require for interest points is the first is it should be invariant, or rather, first I'll write it as covariant. Covariant to rotation, rotation, translation. So if I translate the image by some amount, your interest point should also translate. It should be if I scale the image, the interest point should also scale, and it should be invariant to, for instance, illumination, because illumination changes color. So if you don't have white light out there, if you have some usual lamps, floodlight lamps out there, which are generally orange in color, not exactly orange, but they give a feel of orange, then the color also changes. So we want that to be invariant to color as well. Maybe even the intensity value, because the intensity value depends on how your camera sensor responds to the light. So all these factors, it should be invariant, that you are still able to detect these so-called interesting points out there. So one of the nice applications that was discussed is panorama stitching. So what we have is we have two images, rather I'll just use the same image here. If I take one image which covers half of this part, rather three-fourth of this hut out there, and rest one-fourth, rest the second image covers this part of the hut, then we can find what are the common points out there, or the common interest points between the two images, and based on that we can align it. We can align the two images, and what we get is panorama stitching out there, stitched image. So does anyone remember what is this equivalent to from our previous lectures? Example application is panorama stitching. Anyone? What is this equivalent to? So what are we given in panorama stitching? We are given a set of points which are common in both the images. Yes, at least everyone agrees with that. We'll only check in this common region what are the set of points which are uh, which are useful. For other parts of the region, we don't really consider the points for panorama stitching. So if we have an overlap, just check for that area, and within that area get the interest points, and then get an alignment. So what is that alignment equal to? We discussed that in our previous lectures in the geometry. So that alignment is called as homography. This was discussed, right? Homography estimation. Anyone remembers, recalls it? What is homography estimation? So if we have points on the first image plane as xy1 in the homogeneous coordinates, and in the second image plane as x prime y prime 1 in the non in the homogeneous coordinates of the second image plane, so it can be related by a homography under some conditions. So this is a 3 cross 3 matrix. As you can clearly see that the left and right side are three vectors, three element vectors, and this can be estimated if you are given correspondence. Okay, so here you assume that x prime, y prime, and x and y are correspondences in the left and right image, right and left image, whatever convention. So based on this, you can estimate the homography. Once you estimate the homography, what happens? You can map points from, for instance, left image to the right image. If I call this as right and this is left, although you can change it equivalently. If you can map points from left image to right image, what can you do? So if you just use this specific example, you are taken two images like this. What you can do is you can just map this in such a manner that this can fit like this. So this mapping is what is the homography that we discussed in the earlier lectures. So for that, anyways, so for the core idea is that for that we need interest points out here. So if someone remembers stereo camera setup, do you need to do all these things? Interest points. You need to get interest points and then get the disparity. Is it required? So what happens in canonical stereo? Cano- What happens in canonical stereo? You have one image, and the second image you just move slightly in x-axis. If you consider this as x-axis, so this is the effective movement out there. So once you know that this is just the effective movement is really small, and since you're moving only in x-axis, your correspondences will lie only on the x-axis, and so you search only on the same row as that of the. So if you fix the yellow image, you only search on the same row in the blue image out there. So there you can get dense correspondences. So for canonical stereo, you can get dense correspondences for all. I would not say for all, but for most of the points. Most of the points means points having texture, points within textured region. Can write it that. But in general, you don't have this nice setup where your yellow image and blue image are aligned in this specific way that they are just shifted by a small value in X direction. So what you have to do is have to get the interest points out there. Since here you have every pixel to pixel correspondences, almost for every pixel you have other correspondence out here, but here you have to get those correspondences at first place. And so it's not easy to work here if you don't have an idea of how much the displacement X is out there, or even if you have a rotation, for instance, then it's very hard to use this kind of setup or canonical stereo setup. So you use interest points out there. And yes, one of the applications is homography that we saw here. That was the motivating example in the class as well. So the next is how to find correspondences. So just detecting these points won't help, right? These are all interest points. The point is, I mean, the idea that I want to give you is just detecting those points won't help because they're just a bunch of numbers, x comma y pixel locations on the two images. If you want to match it, you have to give some idea of how does it represent that. How can you represent that specific point? Otherwise, the point is this specific. Okay, just give you one example here. So if there's one point here, and maybe there are a bunch of other points out here. what it can, yes. So what it can lead to is, if you don't have an idea of what to do here, you you have to match one point with every other point out there. Yes, ideally speaking. And that is like an n square. Uh, so for n points in the left image and n points in the right image, the complexity of matching is n square, which you still have to do. But the point is, if you just directly compare pixel locations, it's not good, right? Because here, if you see in the yellow image, it's on the right side of the image. The interest points are on the right side of the image, but in the blue image, it's on the left side of the image. So you have to represent those points in such a way that you can able to match those points. So you need a descriptor. Well, here we are talking about interest point. So once you are able to detect it, so this is the detection part. You need a descriptor. Okay. So once you are able to describe the features, what you can do is you can just so for instance, if a point P1 is described by a descriptor D1, so P1 is just an x comma y pixel location out there with some intensity values. I can just write I of x comma y. The descriptor will contain all these information out there so that it gives you a vector, probably D cross 1 vector. D is the dimension of the descriptor D1, and this descriptor should give you some information about how this pixel value is with respect to its neighborhood. Once you are able to get that distinction out there, you can easily then find how you can easily define that interest point. Once you can define the interest point uniquely, then you can do n square matching out there as we saw and get what the specific match is out there for the left image to that of the right image. Okay. So once you have features, so what you do for a panoramic stitching is first you detect features, and then the next is get the descriptors. With features, what I mean to say is they're the interest points. Once you have the interest points out there, get the descriptors, and then you have to match those interest points based on descriptors. Once you match those interest points, then you can apply the standard homography estimation formula. Well, I will not say formula, but standard homography estimation technique to get the mapping from left to right. And once you have the mapping from left to right, what you have to do is you just have to transfer these points onto the new image and then make sure that your pixel location, which is an integer, have a specific color. If it's non-integer out there, you have to check for the nearby pixels out there, what are the colors, and then just interpolate it based on bilinear or bicubic interpolation. Okay. So this is just a short summary of how to do panoramic stitching. Uh, so interest points also includes finding corners. So corners are the most interesting points if you ask me, because our world is mostly man-made out there. As I saw you, as I gave this example out there, these corners don't really exist in the world apart from seeing in mountainous regions, probably. All other things are man-made structures out there, and we generally keep things in such a way that there are planes in the image. So once there are planes in the image, you will have edges and then you will have corners out there. So most of the focus was on development of the, or rather detecting the corners and edges in the literature. So one of the methods that was given in the class was use an edge detector where USAN stands for uni value segment assimilating nucleus. So nucleus means it's the center point. Assimilating nucleus means whatever nearby pixels out there are similar to that of the center point. Uni value segment means all the values in that specific segment are same as that of the center pixel. That's what it means. Use an edge detector. So if the basic idea is if you have a region out here and you have a detector at a point, rather you're checking whether that point is a boundary. Boundary means it is it a part is it an edge or is it a corner? For that, you're using this USAN edge detector. So at a flat region, all values will be same as that of the center pixel. You can clearly see here. But on an edge, 50% of the values will be same as that of the central pixel. But in a corner, at least for the specific case of rectangle, you're able to see that just 25% of the values are there similar to that of the center pixel. But if you have something, some other shape like this, it's a very bad shape probably. Yeah, if I take a triangle like this, and if I keep send my detector out here, it is it depends on what kind of triangle you're using, but in general, you will have nearly less than 50% of area being covered. Area being similar to that of center pixel. In general, I'm saying. So if you have a weird triangle out there where it's almost flat, then I guess that rule can break down. Yeah. So in this case, you can see it's okay. So this rule can never break down if you clearly see here that until unless the triangle is flat, that all 3 points lie on a straight line, it will always be less than 50%. So you can clearly see that this 50% idea works well out there. And there is a formula out there which which is an intuitive formula that based on the how much area you cover, how much area is similar to that of the center pixel, you can easily see whether this is a corner or not. So of course, this method does not use gradients explicitly. Well, this method does not use gradients, that's fine, but still you're comparing the center pixel to that of the nearby pixel. So it is still capturing what kind of information is it trying to capture? Can anyone tell me? Is it the low frequency information that's being tried to capture or the high frequency? So it still captures the high frequency information since we are checking how different the other pixels are from the center pixel. Yes. So we are checking how much change is out there. So we are trying to capture how much change, how much of the area is similar to that of the pixel. If more area is similar, that means it is a low frequency area, and if less area is similar, then it's a high frequency area. Yes. hope it's intuitively clear. And based on this, the first corner detector, at least I will not say the first, but an earlier known corner detector is Moravec corner detector. So what it tries to do is again measure the gray level difference between a window and window shifted in eight principal directions. So what are the principal directions out there? So if you have a window out like this, probably 3 cross 3 window. Generally 3 cross 3 windows is used, but we can use 5 cross 5, 7 cross 7 based on your specific application and image resolution. So what you can do is if this outer thing is a full image, you can move in all these directions. So there are all these eight directions out there. Once you have these eight directions, so what do you mean by moving in these directions? I will just take this, take this window out there and then place it here. What happens is now I moved this specific central pixel to this direction by one unit. Once this happens, I'll check what are the pixel intensity differences in uh, the corresponding pixel locations. So I'll check this difference, this difference, this difference, this difference, and the central pixel as well. Once we have, actually there are more, yeah. So 3, 4, 5, 6, 7, 8. We'll check for all 9 pixel values out there for a 3 cross 3 window. We'll check for all 9 pixels differences. So intuitively, what we want to detect high frequency parts. And corner is a high frequency part, so we want to detect a high frequency part. So whenever the difference, so the difference is given by what? Summation over the whole window. Anyone? I of x comma y minus I of x plus uh, the window is spanning over x prime and y prime. I'll just put it this way. I of xy minus I of x prime y prime norm squared. So this is the sum of square difference. So if this value SSD value is high, that means there is too much variation out there for in that image, in that specific area per given pixel. That means it's if there is way too much variation out there, it's a corner detector. And if it's not too much of an area which is varying, then it's not a corner. And then the corner is not present. Of course, for this you have to threshold the value of SSD. You have to see how good or bad this uh, SSD is. So if most of the pixels are similar, then SSD values mostly will be close to zero. So if they're close to zero, you should have a threshold much greater than zero to detect to declare it the central pixel as corner or not. So for that, that is an implementation aspect that you need to take care of. What is the good threshold value out there to choose for this corner? But the point is, you can also detect edges out there. Since we are just checking the differences in the patches, so blindly checking the differences in the edges patches. So once we have that difference, we can misclassify a corner as an edge as well. Corner is a part of edge, but edge does not only contain corners. So these specific points, not these specific points, sorry, if you see this image, these specific points are the corner points, but edge contain the other points as well. So what was done is instead of relying on this specific sum of square differences Explicitly, we made sure that we can be more robust to this corner detector. So not we, Harris made sure that it's more robust than the previous one. So we come to Harris corner detector. So what does Harris do? Anyone? So if you remember this thing, here we are taking the sum of square differences. There also we are taking sum of square differences out there. But then what? So this sum of square differences so approximates the SSD using Taylor series. So once you approximate the sum of square differences using Taylor series, you get a approximate with first order. So once you do that, what you get is an expression like this. Your SSD is nearly equivalent to this expression, where U and V are the difference. U and V are the shifts of the original patch to that of the new patch. It is not the pixel location, but these are the shifts. And this matrix M is simply the summation of some multiplications of these gradients. Do you agree? Summation over the window. So can anyone tell if I just see this matrix by itself, do you see any properties of this matrix? What kind of matrix is this? I'm not talking about the matrix M, but the individual matrix of these gradients, which is ix square, ix iy, ix iy square. So one clear thing is it is symmetric, right? But anything more than that? Any more properties of this matrix that you are able to see?
It's singular.
How did you say that?
Its determinant is zero.
Okay. Any other way of explaining it? Yeah, it's singular. You're right, but any other way of explaining it apart from determinant being zero? Isn't it an outer product of the gradient? Ix iy is the gradient along x and y direction, and this is just the outer product. Yes.
Yeah.
So any outer product is a rank one matrix. This is a rank one matrix, and since the dimension of this matrix is greater than one, it's a singular matrix. Okay. So yeah. So we are adding rank one matrices and then taking and then summing it to get this matrix M, which defines the patch around the center pixel. Once you have the patch around the center pixel, then you can say whether that is a specific that then you can use this matrix to define whether your center pixel is a corner or not. And how do you do that? So you compute lambda 1 and lambda 2, or if I say not of this matrix, but of matrix M. Of M. Yeah. So we compute lambda 1, lambda 2 of matrix M, and then what? So your formula is determinant of M minus some K times trace of M whole square to be greater than equal to some threshold. Is this the case? So this was given as R, which is the corner response measure in the class note. So once you have this measure out there, what does this give? Determinant of M, can you write it in terms of lambda 1 and lambda 2? What is it?
Lambda 1, lambda 2.
Yeah, the multiplication of the eigenvalues. And what about trace? Trace of MS?
Sum of the eigenvalues.
Sum of the eigenvalues. Yeah. So once you have these expressions out there, you can clearly see that you can replace these lambda values here instead of determinant and trace. And how does it help? What does lambda 1, lambda 2 signify? Of a matrix M, any general matrix M, what does lambda 1, lambda 2 signify? So if I have a, let this be the input and let this be the output. So if I have a circle here and I applied matrix M on it, that means what? I multiplied all x comma y with matrix M, pre-multiplied with M, and then what I got is this right figure. So if my lambda 1 is greater than lambda 2, I mean, if my x, lambda corresponding to x is okay, and okay, I will just complicating it, I guess. I'll just put it simply. So the matrix M will say how this circle will be distorted in the new space. So this is the new, uh, I mean, the transformed part of the circle, which is now an ellipse out there. So your strength now determines the lambda 1 and lambda 2 and how much distortion happens. And these are the eigenvectors out there. So what you can clearly see from this expression is that they are independent of which direction the distortion happens. They are only concerned about the magnitude of the distortion happening out there. So this means this operator is rotationally invariant. Okay, since it's only dependent on lambda 1 and lambda 2 and not the specific directions out there. So that's one of the major reasons why Harris corner detector became really famous and useful. And there are some other properties that we will go through when we solve the question. Okay. So given these corners, what we ideally want is we want invariances to all of these things. Invariance to intensity change. So this is about detector, by the way. So once we define a detector, we want these properties out there. we want invariance or rather covariance to translation, rotation, and scaling. Intensity, illumination, color, all these will lie for the invariance part. So yeah, after that, Hessian detector was being used, which which at least uh, yeah, which also have these properties of translation. Translation is fine. Rotation, no. So for Hessian detector, the rotation part was not there because Hessian is what? We're just taking second derivatives. If I take a matrix H, which is Hessian, so this is just the second derivative of there. That means you apply this derivative operator Ix twice. What is the general derivative operator that we have been using? Is something like this for in the x-axis, and Iy it will look like this. Okay. Okay. So once we go through these detectors, we moved on to what detectors were actually used in specific applications. The first one is the histogram of oriented gradients. Can anyone tell what was the application for which this was developed? It was mostly developed for object detection. Okay. Yeah. So you want to describe an object. Ultimately, your idea is so to detect an object, you want to uh, see whether the object exists or not. For that, you have to use, okay, the object might be present in a small part of the image. For instance, this is an object, but the other parts of the image is empty. So what you have to do is you have to first, so your main idea is to get a bounding box over the object and then say that whether this object is there or not. Probably you're looking for humans out there, but humans may not be there. There might be trees. So these features are to be needs to be extracted and then checked whether it belongs to the same object or not. So yeah, again, there were gradient computations which were being used to get the boundaries of the objects, and then the main idea is the orientation pinning, which is what they call as oriented gradients. So you can get the gradients using any of the gradient operators like Sobel or Revit. Here, I guess in this case, Sobel was used. And once that's done, so once you have a idea of, once you computed the gradients of the image for each pixel, you divide the image and then make sure that you are able to describe each part of the image by some descriptor. So descriptor using the gradients. So you can do a specific quantization, and so you can divide the image. So your actual image might be even finer, but you're dividing it into cells. Each of them are cells, and each cell contains a bunch of pixels out there. And using those bunch of pixels, so for each pixel, you might have gradients like this. So get histogram of gradients in each cell. Once you have the histogram of gradients in each cell, then you can have multiple cells out there, and then since you have multiple cells, you can concatenate all the gradients. I mean histogram of gradients, probably cell one and then cell two. And what this ultimately gives is the descriptor. So that's the core idea. Of course, there are implementation aspects out there on how to do it. And then once this is done, the point is these gradients are now dependent on how your intensity of the image is, right? So what you can do is you can just normalize it, for instance, to be norm one into norm. The unit the Euclidean norm should be one. You can also take the L1 norm to be one, or some other normalization factors that you can take care of. So this makes sure that even if you have taken it in broad daylight or at night, the descriptors are almost same. So as mentioned in the class, it's not just about what procedures we follow, it's about how much engineering is being used. So for each of these, uh, so for each of these points, for instance, you are doing a histogram, right? So how much should be the binning width? What should be the bin width out there for histogram? What should be the descriptor width? How many cells you should need to take? What kind of normalization is required? All these factors uh, affect how good your descriptor of the object is. And after this, the next descriptor that was done in the class is the SIFT descriptor, which is scale invariant feature transform. So the main idea is to get description of points, description of interest points rather. Here we are not getting a description of full image or the full object as such, but the main idea is to get a descriptor of interest points. Of course, using all those interest points, you can get a descriptor of an object to which it was applied initially. But the point is, you want to define a descriptor of a single pixel instead of full image directly, or rather full object directly. So what again the idea is you want the description to be invariant to translation, rotation, scale. Here we want invariance. So if you remember for detector, I clearly said that we want covariance with translation, rotation, and scaling, but with descriptor, this thing changes. So even if I rotate a point out there, although the detected point should be rotated equivalently, but the description of that point should not change. It should still be the same. That is translation. Whether I translate or rotate or scale, the description of a point should not change. So that's the main motivation of SIFT, why it exists. So given this at a high level overview, it was given that there are four high level algo of SIFT. So what are the four steps out there? So first you need to find the appropriate scale of detection. If you don't find the appropriate scale of detection, then it may not be invariant to scale. So to make it scale invariant, you have to check for different scales what is the actual scale of the key point. We call these interest points here as key points in the specific context of SIFT, since we are only concerned about the points, pixels out there, and not the whole image. So once you have an appropriate scale of detection, what next you need to do is localize the point. Localize why? Because since you are using patches out there, you want to know which exact location the key point should arrive and not a patch out there. So that exact location will help us to will actually keep this. So if you're using any kind of geometric transformations, for instance, it will help you to reduce the errors for the geometric transformation. That's why you want to localize the points as good as possible. The third one is the orientation information, where you would like to get what is the orientation of this detected point. Once that's done, this orientation can help you to. It is similar in spirit of this histogram of oriented gradients, so that this can help you to get a good descriptor of what the key point says, and then the last is the key point description. So for the key point description, we need these properties: invariance, translation, rotation, and scale. Okay, so for scales, they use pyramids, which we'll discuss. Probably discuss a question. Yes, we'll discuss a question out there. Um, and then once scales are detected, you have to localize the point, which is done with maxima in the scale space. So once you have the maxima in the scale space, you can do orientation assignment using gradient information out there. Once you have gradient information out there, you can use the descriptor. You can create a descriptor with these gradients. Okay. But the gradients, as used similarly, that you will divide the image into cells, and within each cell you will have multiple pixels, and using those multiple pixels you will define a histogram and then get a description of how the key point looks like. So why is this specifically useful? Again, you can use this shift kind of features to match it and use it in the panoramic uh, mosaicing or the homography estimation that we were discussing previously. You can get the structure of the 3D world as well, because for getting the structure of the 3D world, you need to know which, uh, given a 3D point, where is it in the two images or multiple images out there. So for these things, you generally use shift key point detector out there. And of course, object detection is one of the examples that has been shown in the class. So it can also be, if you are able to get specific key points out there of an object, you can concatenate those description descriptions in an appropriate manner and then see whether it's useful enough to get the other object out. Okay, so given this summary of previous lectures, we'll start with the questions. Any doubts as of now? Okay, so this is my first question for today. You're given histogram that contains 9 bins corresponding to angles this 0, 20, 40, 60, 80, 100 to 160. Okay. Given gradient magnitude and direction. So this is the magnitude out there, and this is the direction in degrees. Compute the vector representing histogram of gradients corresponding to the following details. So you're given the histogram bins out here, and you're given this uh, magnitude and direction. So you have to use histogram of gradient features. So these are the features that you have to use. How do you compute the vector representing the histogram. So these are the HOG. So what do you do to get HOG features? Anyone?
You add the magnitudes for every bin.
Yes, that's the core idea. Magnitude of the gradient. So first you have to compute gradient. Since gradient is given, so we'll directly move on to the next step. That uh, yes. So this is the magnitude and this is the direction. So what are the available directions here? So for 40 degrees, you have magnitude as 7. For 80 degrees, you have magnitude as 2. And for 100 degrees, you have magnitude of 3 plus 4, which is 7. So how will the vector look like? So your vector should uh, represent these elements in this order. Yeah, okay, there's no 180 there. So what will we do? For 0 degree, there is no magnitude, so it's 0, 20, 0, 47, 60, 0, 80 is 2, 100 is 7, and others are 0. So your vector will look like this. Is this fine? So the core idea is add the gradient magnitude. So do you think if I need to get HOG features between two images and then try to match the object between them directly, is it good enough?
It should be normalized too.
Yeah, so yes. So you have to normalize the image before you take the gradients and then compute this histogram. If you don't normalize the image, your histograms will look similar, but they may not be the same in terms of values. So one easy way I can clearly see here is you can just make this as a unit vector and then match between the two images, or else you can just normalize the image out there so that they lie between the values, intensity values lie between a specific range like 0 and 1. So correspondingly, your gradient magnitudes will also change, and then both of the histograms will be the same if they contain the same object. Okay, so we move on to the next question. Any doubts to the first question? Any doubts? Then so here you have to find the Harris corner strength or the corner score that was discussed in the class. What's the specific name? Corner response measure. Harris corner strength or corner response. So for this, what is it that you need to do? How do you get the Harris corner strength or corner response measure?
Obtain the matrix M. So for that you need Ix and Iy.
Okay, yeah. So for that, we'll need Ix, which is the gradient along the direction x, given like this. So how to get that? So I'll place this specific thing, rather the kernel, in this direction. and then just check what is the output. So for this 3 cross 3 area, what I will get is this is 2. This one will be 2. If you place it here, if I place it here, it's again 2. Right? Yeah. Okay. I think everything is 2 here. And then again, I have to do that for y direction. Y direction is generally in this specific direction. It is vertically downwards direction. Once again, you have to place this kernel out there like this. So I guess here 10. Oh, okay. Everything seems to be 10. Okay. So once you get ix and iy, what is that? What is it that you need to do? Yeah. Someone said we need to get the matrix M, which is ix square, ix iy, ix iy, and iy square. So we saw that this small matrix is symmetric and is singular because it's a rank 1 matrix. So the capital M matrix is also symmetric. So will it be singular or not? Anyone? This is symmetric and rank 1. What about this? This is symmetric because summation of symmetric matrices is a symmetric matrix. What about being what should be the rank of M? Anyone? So it so rank can be greater than equals to 1. It can never be less than 1. Oh, maybe it can also be less than 1. Okay. I should not specifically say this. But you cannot comment on the rank. Cannot comment. It depends on the values. So in general, the values are such that for practical purposes, the rank will increase and the matrix will have a rank 2 in this case, since it's a 2 plus 2 matrix. But you can have some specific values for which matrix rank can still be 1 or it can still go 0 as well. So we cannot comment on the rank of the matrix. Okay. Yeah. So yeah, what we need to find here is we have to sum all the gradients, we have to square the gradients in x, and then sum them, you have to multiply the gradients and then sum, and then you have to square the gradients in y, and then sum them. So what happens here? It's 2 square into 9 here. Here it's 10 square into 9 because there are 9 elements out there. Here it's 20 into 9. So all this should be what? 36, 180, 180, 900, which is fine. So this is the matrix M out there. Once you get this matrix M, what is the next step? You have to find the Harris corner strength or corner response measure. So the corner response measure is, I think, given as R, which is determinant of M minus K times base of M whole square. What is the determinant? It is 0. And for Harris corner strength, you take can take K as 4. And what is the trace of M? It is something 936, right? Just adding the diagonal elements. So given this, what are the properties of a what properties of Harris corner can you use to determine whether it's a corner or not? What properties of the score can you use? Telling this as a score, which is corner response measure. So, what properties of this corner response measure can tell you whether this is a corner or not? So, for flat region, what should be R? Anyone? So, does everyone remember this specific diagram that was given in the class? So, this is lambda 1 and lambda 2, something like this. This is one region, how other regions as well. So, yeah, can you tell me what this diagram represents? This one is both lambda 1, lambda 2 is low. Lambda 1 is low, lambda 2 is low. What does it mean?
Flat.
Yeah, flat because low variation in both directions. Low variation in both directions. So it is flat. What about this? This is lambda 1 much greater than lambda 2. This is,
Edge.
yeah, it's an edge because
High variation in one
one
direction.
direction. Yeah, high variation in one direction. Again, same, this also is an edge because of the same reason. And this is both lambda 1 high and lambda 2 is high, which means it's a corner. So if in all the directions your gradient is changing way too fast, what does it mean? That means it's a corner. If in a specific direction gradient is changing and other specific direction gradient is not changing, then it's an edge. So for instance, if I take something like this, using the class example, if I take lambda 1, these are not the principal directions, but for both the cases, it will lie in this region. For cases where we just have edge out there, it will lie in this specific region. So if you take, for instance, the same lambda 1, lambda 2 here, lambda 2 will be very high, lambda 1 is almost 0. And if there is nothing out there, then you take this principal direction, you see there is no response coming out. It's nearly 0. So it's a flat region. So given this diagram, how can you represent it mathematically? So for flat region, determinant of R is close to 0 or very low. Since determinant of R is determinant of R, okay, I will not say determinant of R, it's the absolute value of R. R is scalar here. So it's an absolute value. So the absolute value of R is low for a flat region. What about edge? You can see that for edge, one of the lambdas will be very low, so it is close to zero. So your determinant will still be zero, but your trace will be high because one of the lambdas will be high. So given that your overall value of R will be negative, R is less than zero, gives you an idea of edge. Okay. What about corner? Since both the lambda values are high, determinant is positive and this is also positive. So it's if it's a strong corner, it's clearly greater than zero. Why? Because this is lambda 1 into lambda 2. This is lambda 1 plus lambda 2 whole square. At raise square. Yeah, this is the determinant. If you just replace it here, this turns out to be the case. Is it clear? So what this specific value says is the determinant is zero and you have a negative value of the score R. Negative value means what you have here is an edge. This is our this is the region. This region contains an edge. All right. Is this clear? Okay. We move on to the next one. So you are given 5 cross 5 feature matrix, and then you have to apply HOG feature descriptor with 3 cross 3 Sobel kernel. So again, Sobel is the high pass filter or the kernel which computes the gradient. The gradient orientation of the central pixel will be what? Okay. So how to solve this? How first we need to know how Sobel kernel looks like. Anyone? Yes, anyone?
1 to 1, and then minus 1, minus 2, minus 1. The bottom and top rows.
So for which direction it is?
For x. For vertical, yeah.
Vertical is one. This is for y direction. And for x direction, it is just have to rotate it by 90 degrees. So the same thing like this. So what you need to do, you have to find the gradient at the central pixel, gradient orientation at the central pixel. So what is it that we need to do? We'll take this area. We'll take this area and then we'll use this kernel to get gradient along y direction and x direction. And then so we'll first get the gradient along y direction, which is just applying it directly and then it's 136, 17, 170 minus 255 minus 85 minus 170. What about g of x? It is okay. I did something wrong. So it is 136 into 1, 17 into 2, and 170 into 1 from this corner. This is 255 into minus 1, 85 into minus 2, and 170 into minus 1. This is how you compute the gradient along y direction. For x, it is 170 plus 136 into taken this part. Now I'll take this part. So this minus 136 minus 0 minus 255. So given this, how will you compute the angle? So the theta is tan inverse of gy by gx. Alright. Once you place these values gy and gx, it will give you the specific orientation of the central pixel. So this is what they are looking for. Is it fine? Okay, I guess it's fine then. We'll move on to the next one, which is pretty simple question. You are given a Hessian matrix at an edge pixel of an image. Compute the ratio of its largest and smallest principal curvatures. What is largest and smallest principal curvature? Anyone? So this Hessian matrix is just computation of Hessian. That is the second derivative along x direction, along y direction. Here it's the mixed derivative along x and y direction. It's the same Hessian matrix that we were talking about. So for principal curvatures, what you need to get? You need to get the eigen values of the Hessian matrix. That's all is required, right? So if you take, you have to solve for this specific equation, h minus lambda, determinant of it should be 0. So if I write it explicitly, it's like this. Determinant of interest should be 0. What does it look like? Okay, this is a very nice. Uh, expression. So this turns out to be like this. Yes. So lambda should be like this, which is 1.1 or 0.7. So once you get the eigenvalues, what is it that you need to do? Ratio of the largest and smallest principal curvatures. So lambda gives us an idea of the largest curvature. Of course, if you now get the eigenvector, it will give you the direction as well of what is the direction in which the curvature is maximum and then what is the direction in which the curvature is minimum. But here we just need to get the ratio. So if I call this as lambda 1, this is lambda 2, what we need is lambda 1 by lambda 2, which turns out to be 1.57. So is this question clear?
Yes.
So whenever in general, when you see curvatures out there, principal curvatures out there, it's generally computed for a Hessian matrix or the Hessian of the function. Here the function is the intensity values of the image, but it could be anything in general for in maths. Okay. So we can move on to the next question. are given a bunch of matrices out here. Yeah. Okay. Yeah. I will just write it. 8. This is 8. 10. This is 10. Okay. Yeah. So you are given below a set of output after applying Gaussian filter on the image with different bandwidth for a single octave. Okay. In the shift detection algorithm. So once you are given these matrices, find the key point, location, and scale. Okay. So this is what you need to do. Find the key point, location, and scale. So they have done some part of the shift algorithm itself. They have taken the images and they have applied Gaussian filter already for us. Once we have Gaussian filtered images, this is the set of Gaussian filtered images. So these are the set of Gaussian filtered images. And then what they want, we need to find the key point, location, and scale of this problem. So how do we proceed? What does shift do after this? Once you have Gaussian pyramid out there, what is it that's done in shift? So this is the first part of the shift where you need to find the key point location as well as the scale, appropriate scale at which you want to work on. How is it that you do? Anyone? So if you remember the diagram, it looks something like this. So first we have the original image and then we'll have apply Gaussian blurring up to some levels. Up to how many levels before we decrease the size of the image? Up to the level in which the effective blurring with Gaussian is greater than 2 pixels. So once you have it greater than 2 pixels, then that means the effective sigma effective of the Gaussian, the standard deviation of the Gaussian is greater than 2 pixels. Once you have this, then you can reduce the size and then you can again do blurring out here. So this is how the Gaussian pyramid is created. Once you create this Gaussian pyramid, then what is to be done? Then you take the differences of this individual uh, Gaussian blurred images. So once you take the differences, what happens is effectively seeing what kind of high frequency information is there in that image. Yes. What we need to find? We are doing it in the shift detection algorithm. The shift detection algorithm detects what? interest points like corners. For corners, you need to get the high frequency information. For high frequency information, you will have to look at the, you will have to use a kernel which gets you the high frequency information. Instead of using Laplacian of Gaussian directly, this also approximates, this is what? This is difference of Gaussian. The difference of Gaussian approximates Laplacian of Gaussian. That's why this is being used. And this is computationally cheaper than applying Laplacian of Gaussian on each of the images, especially when you have a pyramid out there. So once you create Gaussian pyramid, you take differences of the images. So this is DOG instead of the usual DOG out there. So once you get the differences of images, then what? Then comes the part 4 key point localization. That means you have to get the key point out there and the specific scale. So I just redraw it for convenience. So these are the Gaussian. This is the Gaussian pyramid. So once we take differences, so how will it look? You will have a pyramid of difference of Gaussian. Difference, so if you put a minus sign, this is difference of Gaussian pyramid. And then what you need to do? You need to find the scale space extrema. Find scale space extrema. Extrema includes both minimum and maximum. So what you need to do is you just take so if this is your center pixel out there, what I can do is I'll take one level above, one level below, and the level itself as well. And what this effectively gives me is a 3 cross 3 cross 3 matrix centered around the center pixel that we are interested in. So once we have this 3 cross 3 cross 3 matrix, we'll check the maximum value in this matrix, maximum linear value, since we want extrema. This is check extremum values in this 3 cross 3 cross 3 matrix. And once you do this, wherever the extremum value lies, this is the specific scale. Rather, if I put it here, this is scale 1, this is scale 2, this is scale 3. So if your extremum value lies in scale 3, this is the scale at which your your key point lies. Get the scale at which the descriptor lies. This is the first thing, and the next thing is the location of extrema gives the location of key point. So that's what the shift feature. That's how you get the. Uh, that's how you the shift detector part works. that you get the scale at which the descriptor lies, and then you choose the location of the extrema given the location. The location of extrema gives the location of key point. So why are you checking both minimum and maximum? Because in terms of magnitude, one can be higher and one can be very low. So ultimately, you have to get the maximum magnitude. In the sense, you'll not really check for minimum and maximum as such, but maximum magnitude wherever it lies, you get the scale at which that maximum magnitude lies and the location at which the maximum magnitude lies, and that's it. That's how you get the location, key point location and description. So for this specific uh, question out there, so here it was 8, 8 and 10, 10. So for this specific question, what you need to do, whatever steps I told here, you just need to do that. First, take the difference. So once this is the difference out there, since this is what? This is the Gaussian pyramid. Once you have the Gaussian pyramid out there, you just take the difference. Once you have the difference, you have some values here, element-wise difference out there. You get some values which gives you the difference of Gaussian pyramid. So once you have the difference of Gaussian pyramid, then what next? So now think of it as a 3D volume where each of these lie here. So this one lies here, and this one lies here, this one lies here, things like that. This one lies here. So this is like the 3D volume out there. And now you have to check for the specific uh, patches nearby this, above this and below this as well, and get the extrema. So if I think I computed this values. So the patch value, I mean the lowest number will turn out to be 15 among all these cases, and the coordinates will turn out to be x equals to 1, y equals to 1, with scale as 2. So here this is scale 1, this is scale 2, this is scale 3, and this is scale 4. Okay. So any doubts on how to approach this question? Okay. Okay. So I guess this gives some clear idea about how SIFT detector part works.
So for finding the extrema, we take every pixel as the center pixel and then check for if it is the maxima or minima in the volume.
Yes. Yeah. Yes.
Okay.
So yeah, that's how the algorithm works. That you check for every pixel out there and get the maximum minima in the whole volume. But here in this specific case, I mean, if you're relating it to the exam, then you'll just check for the maximum minima over the whole patch, since it's same, right? If you take maximum minima over these three patches after doing the the differences, it will be same as, and then you check for these three patches. Since you have to represent this whole 4 cross 4 patch with a single number, so should be, it should give you a single output. In the options, you'll get a single output, which is the minimum maximum magnitude. Okay. Okay. So the next one is a pretty simple question, I guess. So you're given a 3 cross 3 matrix, compute the Laplacian of the central pixel using finite difference approximation of derivative. So how do we proceed with this? How does the Laplacian look with finite differences? Anyone? So if anyone remembers, the first difference is f of x plus 1 comma y minus f of x y. And the second difference will be f of x plus 1 comma y minus 2 times f of x comma y plus f of x minus 1 comma y. This is in the x direction. Yes. So this is first derivative and this is the second derivative. The effective here is in x direction is 1 minus 2 and 1. Right? What about for y direction? Actually 1 minus 2 and 1. So if we combine both of them, what we get is this the specific operator. This is the Laplacian operator. Laplacian kernel. Yes. Is everyone fine with this? So we are just doing double differentiation along x direction and then y direction, and what we get is this specific operator. I think this specific derivation, how it how the Laplacian emerged, gets you an easy way of remembering this. Okay, so what we need to do, we just have to apply this onto this at the center pixel, right? So what is it? The answer okay, it is 56. When I take this one and multiplied with this is 80 into 1 plus 59 into 1 plus 40 and minus 4 times of 30. Yes, everyone agrees. Hmm?
Yes.
Okay. Yes, yes. There and then whatever. 115. So this turns out to be 115. Okay. So this is the answer. Answer is 115. So when you apply this Laplacian operator onto this 3 cross 3 matrix, what you get is this response from the Laplace operator. Okay. Any doubts in that? Okay. So move on to the next question. Which of the following statements is or are true? Harris corner detector is rotational variant. Is it right or wrong?
Wrong. Right.
It's rotational invariant. Yes.
Yes.
How? So if you remember the score that is given by determinant of m minus k times trace of m whole square, which is, you can rewrite it as lambda 1 lambda 2 minus k times lambda 1 plus lambda 2 whole square. So these lambdas, even if you rotate the image, it will still be the same. It's just the direction in which at which the it's the eigenvector which changes, but the magnitude still remains the same for lambdas. So since it's independent of directions, it is rotationally invariant. So this is false. What about the next one? Harris corner detector is invariant to affine intensity change. Is it right or wrong? What do you mean by affine intensity change? I prime is A times I plus B. This is an affine transformation or intensity change. Yes, of course. Now A and B should be in some within the scale such that I prime also lies between 0 to L minus 1, where L is the max uh, number of intensity levels. So if this is ensured, then A and D are valid affine transformation out there. Yes. So do you
Mm.
think affine Harris corner is invariant to affine intensity change?
It's partially invariant to the uh, 2 plus b that will get cancelled away because of the derivative, but the scale parameter will remain a.
Yeah. So this part it is invariant. Um, okay. What you are saying, this part is variant,
Covariant.
covariant. Yeah, that's correct. So this scaling part is covariant and the shift part is invariant. So ultimately, it is not invariant to affine transform. So it is false. Everyone agrees. You can just see from here that if I scale the intensities, this lambda 1, lambda 2 will scale appropriately. So this doesn't make it invariant to the scale changes. Okay, so the next part is about the shift detector. Yeah, the detector part. The scale factor by which each image differs from next image in an octave for shift operation is 2.0925. You think it's right? No? What is the scale factor that we are talking about? So, if you remember this, sigma s plus 1 is 2 to the power s plus 1 divided by s, or rather 2 to the power I by s. Yeah, this is better. Times sigma naught. So this is the initial sigma of the Gaussian, what you are effectively doing is if you apply this repeatedly, 2 to the power 1 by s times sigma. If you apply this repeatedly, what happens is you are increasing the sigma with ith scale out there. Once you increase the sigma with ith scale, you generally make sure that this value is less than 2. So that if you remember this diagram of octave, this is the diagram of an octave. So before changing the scale, here at this level, your sigma should be 2 pixels, effective sigma. What do I mean by effective sigma is this left hand side. Here this should be sigma of I, not sigma s plus 1. This is what I am saying is the effective sigma. This effective sigma should initially be less than 2, but you have to, but if you repeatedly apply the Gaussian blurring out there, you will cross a point where the effective sigma increases more than 2. Once that happens, you can decrease the image size and then continue. So this thing is called as an octave. So within an octave, your scale size should of course be less than 2, right? What about the question that they give? The scale factor by which each image differs from the next image in an octave is 2.0925. So it is greater than 2, which is false, right? If it's greater than 2, your octave will only have one image, two images rather, the first and the last image. And as soon as you reach here, since it's greater than 2 pixels, you will reduce the image. So you won't really have three uh, layers at which you can compare your extrema, scale space extrema. So you cannot really apply the shift algorithm if you don't have the factor less than 2. So this specific factor, this multiplicative factor 2 to the power I minus I by s, since I is always less than s, not always less than s. So the intermediate for intermediate ones, intermediate scale, the I is less than s, which leads us to this specific expression. So this is less than 2. So this is false. So your answer is none of these. Is it fine? Any doubts? Okay. So we move on to the next one, which is USAN. What is USAN? We just discussed in the class at the start of the class, which is univariate. Uh, Even I forgot, I guess. Let me see. Yeah, univariate segment asymmetric assimilarity nucleus. Assimilating nucleus. Yes. So as I said, assimilating nucleus means how close is it to the central pixel. Nucleus means the central pixel. Assimilating means how close is it to the central pixel. Univariate segment means how close the whole patch, whether the patch has similar values or different values to that of the central pixel. That's how the word came. Univariate segment assimilating nucleus. So the USAN area of the corner of the images at the corner of the image is what? Is it similar to the template area? So if you remember this specific example in the class, so what they are asking is if your template is like this, which is circular, and you have three different regions, for instance, here it's a corner, here it's an edge, and here it's a similar, it's a flat region. So how should it be at the corner of the image?
Less than half the template area.
Yeah, it should be smaller than half of the template area. Since that time we looked at it. This is the effective area, which is similar to the central pixel out here. Here, for this case, if you are on an edge, the effective area is half. If you are outside an edge, the effective area, which is similar to the central pixel, is the whole area. It is similar is wrong. Half, half is an edge. This is flat region. This is an edge. This is smaller than half of the template area. So this is a corner. Smaller to one third of the template area is can also be a corner. But this is more generic statement that as soon as you see that it's smaller than half of the template area, then it's a corner. So I gave you that triangle example that here as well, your area is smaller than half of it. It's not necessarily one fourth. It can be more than one fourth. If it's an equilateral triangle, it will be one third of the area. But still, you see that it's smaller than half of the template area. So this is the most generic answer. So this is the right answer. Is it clear?
Yes.
Okay. So this is the last question for today that I have is on Moravec corner detector. So which of the following is true for Moravec corner detector? So what is Moravec corner detector? I just explained at the start of the class. So it uses sum of square differences uh, of what? Of the patches and all the principal directions. So once you have the patches in the principal directions, then you see wherever the lies, maximum of SSD lies in that direction. You can say that if there is if there is a maximum out there, then you can say that there is a corner or corner present, or the corner is detected by this Moravec corner detector. Okay. So we'll move to the options. If the windowed image patch is flat, then all shifts will result in a big change. Is it right or wrong? So since you are somewhere here, if you shift somewhere here, if the image is flat, that means all the pixels are similar, then what? All shifts will result in a big change. Yes or no?
No.
No. Yeah. Because all of them are similar, the sum of square differences will be very small. So it is false. So how do you are using sum of square differences? You are taking the corresponding pixels and then just taking the differences. So for 3 cross 3 patch, you have 9 values of differences out there. Okay. The next one is pixels which exceed a local maxima are chosen as interest point. True or false? So you are ultimately finding the differences where there is a maximum out there. So for a given central pixel, if the sum of square differences are high compared to other pixels around around the central pixels, that means if you have a patch here, you fix this. If you have a 3 cross 3 patch, for instance, like this, if you fix it here, then you'll check nearby regions. If you fix it here, then you check nearby regions like this. Again, if you fix it here, you check a nearby region like this. The point is wherever you get the SSD maximum. So, for instance, if your SSD is maximum at this pixel location rather than other pixel locations, then you choose that one as corner or rather interest point. Yes, because this pixel is way more different than the nearby pixel. Yes, so it is true. What about the third one? If the windowed patch is an isolated point, then all shifts will result in a small change. What about this? So if you have an isolated point, this is an image, this is an isolated point on it, and if you use a window on top of this, move in any direction, sum of square differences is high, right? Isn't it? Because they are not the patches are not similar at all. So if you move in this specific direction, the patch is very different from the yellow patch. Okay. Again, if you move in any other direction, the patch is very different to that of the yellow patch. Since the patches are different, it will result in a large change. So this is false. And is it rotationally invariant? No, of course this is also false. Why? Because you're using patches out here. Once, as soon as you use patches, if I rotate, if I rotate to some other extent, then it is possible that your SSD may not be maximum since we are only checking this direction. So whenever you use patches directly on images, it can never be rotationally invariant. Okay. So your answer is this one. The pixels which exceed a local maximum are chosen as interest point. Okay. Any doubts with this question? Okay, then I guess that's all I have for today. If you don't have any doubts, we can stop the session here. Okay, thanks for joining. I'll see you next week, same time.
Okay, thank you.
Okay.
So I want to ask one question
Yeah.
regarding the image segmentation.
Okay.
So if so if we get so if we have a data set consist of NEXA images which are really which are not properly emitted, in which some of the images are not properly emitted, some of them are cloudy and some of them are noisy.
Cloudy,
We
you're
can
saying.
so how we can segment it, because some of the because we can remove cloudiness and noise from the images and no emission to a certain point.
Mm-hmm.
So which segmentation technique is best for that?
For cloudy image, you have to somehow remove the cloud or remove the noise. Segmentation will not work on noisy images.
Yes, I know that, but for that I have to remove the noise. But after that,
After
with
removal of noise, you can just use the morphological operations that you will do. If
okay,
the noise is removed effectively, then
Hmm.
only you can assume that your morphological operations will help you.
Okay, okay, thank you.
Yeah. Okay. Okay then. I'll see you people next week.